Hello, once again. Thanks for joining us on Space Nuts, where we talk about astronomy, space science. We share recipes. We do all sorts of things. And on today's edition, we will be talking about a whole bunch of stuff because we're dedicating the whole show to audience questions. So questions about white holes, hypothetical cue sticks punching people from Earth to Mars, singularities or lack of, a big rip, drilling a tunnel through Earth and jumping in. That's somebody's idea of fun. And where's the nearest sun-like star and how many are there? We will answer those questions and much, much more today on the latest edition of Space Nuts. Stick around.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as he always does because he can't help himself, is Professor Fred Watson, astronomer at large. Hello, Fred.
I think you've hit the nail on the head there. Space Nuts is not a job, it's a illness. It's because you can't help yourself.
It's a lifestyle.
A lifestyle.
Yes. Well, we got a lot of feedback from people who log in every week to listen because they don't want to miss it. So that's good. Really nice to get that kind of feedback. It's going to be a busy program, so we might dive right in. But before we ask our first question, I know you wanted to raise an issue about a fire in the United States.
Oh, yeah, just to catch up with it. Yes, so the National Observatory, the National Optical Observatory, which is at Kitt Peak, which is not far from Tucson in Arizona, have undergone something very similar to what we at Siding Spring Observatory underwent back in 2013 when a bushfire swept over the mountaintop and burned lots of vegetation. The same thing has happened at Kitt Peak a few days ago with a similar outcome, we understand. Now, it's a bit early to say because it's too soon for the astronomers to return to the site. It's still a danger zone. And we experience the same thing too. But it looks as though they've had the same issues that we have, that the telescopes themselves have survived. And because it actually includes a very large telescope, one similar in size to our Anglo-Australian telescope. But they've lost some of the auxiliary buildings. And I think that includes the astronomers' accommodation, which is exactly what happened at Siding Spring. We lost the astronomers' lodge. And in fact, we lost a couple of other buildings, including the fire station, believe it or not. That was another one that had to be rebuilt. But we survived. The telescopes all survived in good order.
Well, I was working for the ABC at the time, you might remember, Fred. And
yes, you were. Yeah, that's right.
We had our transmitters on a neighbouring peak. And I think I've mentioned before that they bombed them with retardant and turned the whole top of the mountain pink to try and save the transmitters because the police and the ambulance and rural fire service, all the emergency transmitters were up there. And they saved them. The fire went over it, but everything stayed unscathed and we stayed on the air. I had to send a team of reporters up there to cover the fire, and it was pretty scary because we really sent them in there without knowing if we'd be able to get them out, not because their lives were in danger, but because of the way the fire was tracking and the way it was going to cut the roads off. And we ultimately had to bring them home early, otherwise they wouldn't have got through. It was pretty terrifying state of affairs.
It was grim.
I'm sorry to hear that's happened. I was just looking it up and it's in all the astronomy, on most of the astronomy websites. But they're saying that the worst case scenario has been avoided, which is good, very good. All right, let's get down to business, as I say, and we're going to do sort of a mix of audio questions and text questions on the show today. And this first one is a topic that comes up from time to time about white holes, but this is a different spin on it.
Hi, this is Buddy Bear again from Oregon. I was wondering if the Big Bang was possibly a white hole and that the reason the universe is still expanding is because we're living on the inside of a white hole, and it's expanding because it takes up all space, the exact opposite of a black hole. Sorry about my earlier recording. I have never done this before. Thank you. Big fan.
Thank you, buddy. I'll give you a radio lesson, buddy. Never apologize for a mistake because people won't remember it anyway. So, I heard what you were talking about it when I was going through all the audio questions, and seriously, it's not that big a deal. So just don't worry about it. We got what we wanted, and happy to answer your question. Yeah, are we inside a big expanding white hole, Fred?
I do like the idea, that somehow the universe is connected to a white hole. The normal, of course, we don't know that white holes exist. All we know is that they are mathematically possible. That's what a white hole is. It's the same as a black hole, but in the equations that describe it, you reverse the direction of time. So that's that, and you get a white hole, something that doesn't suck anything in but spits a lot of stuff out. And I guess that's where everybody's coming from on the issue of the expanding universe. On the other hand, conjecturally, so I suppose philosophically, I have an issue with the fact that white holes probably do have an event horizon, a bit like the black hole, but it's white rather than black because stuff's coming out of it. And so if we're within the event horizon of the white hole, I don't know what we would necessarily see. I think, I suspect, since I've not read in any of the learned journals about the notion that our universe might be a white hole, that there is some theoretical reason why this can't happen. But I personally think it's rather a neat idea. Yes, I'll check it out, just in case anybody has come up with the theoretical framework.
Well, I do suppose the fact that we've never, ever found a white hole could lean towards the possibility of the whole universe being one.
Yes, that's right. But on the other hand, it's got a lot of black holes in it. We do know that. So can you have a black hole within a white hole? There's a philosophical question.
That is a really interesting question. But
I suspect the answer is no.
Yeah, possibly not. Yeah. But, I don't know. We're going to be talking about billiards next. So it's, there's...
Okay.
Could be. We could be just on a giant snooker table. And what we're seeing is not stars and galaxies, it's billiard balls. But unlikely. But, Buddy, thanks for your question. Possibly not is the answer.
Yes.
Possibly not.
It's the nearest thing to
Okay. Now, Fred chose a few of his favourite, well, they're all good questions, but a few that he wanted to tackle today from our text writer-innerers. And he chose the ones with the most amount of text for me to read for you. Including this one from Pete in Marmong Point, which is in Australia, a lovely piece of the world. I have a hypothetical question which I'm confident couldn't happen in the real world, but not sure which laws of nature would invalidate the scenario. And I fully accept that dealing with the minor practicalities such as planetary rotation and movement around the sun, Milky Way, etc., would have to be taken into account. However, for the purposes of this question, I'm assuming we can do this exercise in a theoretical split second. So we need to start with the idea of having a super thin and long billiard cue that could reach from Earth to, say, Mars. And then at the end of the cue, there would be a billiard table with a ball just waiting to be pocketed. With the time for light to travel from Earth and Mars at minimum distance being 182 seconds, if I move the cue ball at the Earth end, does the cue end hit the ball immediately, even though we wouldn't see the ball move for 182 seconds? I'm thinking that maybe there is compression of molecules at the cue that means the Mars end doesn't move immediately. But maybe the whole premise of having an object long enough that could physically reach that far is simply not possible. So which laws set the practical maximum distance? Appreciate you getting this far with my fanciful idea. At least it doesn't involve black holes or the James Webb Telescope. Thanks for the great podcast, Pete Marmong Point. I know where he's coming from. So would it happen instantaneously, but we not witness it for 182 seconds, given the time light takes to travel?
No, is the answer.
Oh.
Because, so if you can apply the normal laws of physics to this very, very long billiard cue, you push it at one end and that compresses it. And so the thing is long enough that what you're doing effectively is setting up a sound wave in the billiard cue. Your pressure push gets transmitted down the billiard cue and takes however long it takes for the speed of sound to get to Mars, which is a long, long time.
Right.
And then it pokes the ball at the other end when it gets there. So it's the speed of sound through the billiard cue that is the the crucial giveaway. I've read quite a bit about this because it's such an interesting hypothesis, but there is another suggestion. Supposing you had an infinitely rigid billiard cue, would that work? And the answer is no, because there's some sort of issue with the electrical potential of the atoms in the stick, because it's infinitely rigid. The summary I've read here says that every atom would have an infinite electrical potential with every other atom in the stick. And this, regardless of what the stick was made of, would in turn make it infinitely massive. The bond between the atoms will be so strong that once you've made this infinitely rigid stick, every atom would have enough energy to break free of the confines of the stick, and it would probably instantly disintegrate.
Wow.
So either way, you've had it. You're not going to poke the thing faster than the speed of light.
Okay. That's fast. It makes sense when you think about it, because nothing can go faster than the speed of light except the expansion of the universe. But it's an interesting scenario. And yes, there are other things to take into account because of the movement of the planets and the rotations and the orbits.
That's ignoring all that stuff.
You'd never be able to keep it straight enough. And we're also assuming that Pete's good at billiards. He might have missed the ball.
Yes. He might. I guess actually, just so I think one of the aspects of Pete's question was, how is there a practical maximum distance for a long object? And I guess the thing that comes to my mind is the idea of the space elevator, Andrew. Where you've got,
I was thinking about that.
Something connecting a point on the Earth's equator with a satellite at the geostationary point above the equator. But that's not a rigid thing. That's something that's quite flexible, that's kept in place by effectively centrifugal acceleration. And of course, in terms of practicality, there is no material yet known that will withstand the forces that you need to keep that thing up. People have proposed all kinds of interesting, materials, like making it out of buckyballs, these carbon molecules and things of that sort. But I think at the moment it's regarded as impossible.
Oh, okay. Yeah. All right. So there's another little science fiction thing that hasn't happened yet, but
yes, that's right.
Yeah, it probably will one day, as will artificial gravity.
Yeah, except maybe it was a conversation I had, and this is the only name I'm going to drop in this conversation, with Buzz Aldrin once at dinner.
I've had a conversation with him.
I know you have. Yeah, I know you have. Anyway, and Buzz made the comment that it's never going to happen because of space junk, that you've always got stuff, orbiting debris, which will essentially cross where the space elevator is. It's got to be on the equator. Every spacecraft crosses the equator twice per orbit. So, you're always going to be really pushing against the odds.
Yeah. That makes perfect sense. We've messed it up out there and probably put ourselves in a situation where even if we do develop the technology to create a space elevator, we can't build one without getting it smashed up, unfortunately.
Yep.
All right. Thank you, Pete. Let's move on to an audio question. I'm not sure who this is from, but we liked it because it brings up a problem that Fred is going to solve for us.
I love your podcast. It's got me interested in astronomy again. I built a telescope with my dad back in the 50s. I actually did the grinding on the mirror. And I ended up building my own in the 80s. I've heard all your podcasts. And my question is about singularities at the center of black holes. What do you guys think about us not even mentioning what's inside a black hole, since general relativity doesn't really talk about anything beyond the event horizon, and we don't have a quantum theory of gravity. So talking about singularities has always bothered me. It just doesn't make any sense. Thanks, guys.
Okay. Thank you. Yeah. So he's got a problem with us talking about singularities.
Yeah.
It's an interesting dilemma, and I think you're agreeing with him.
Yeah, I am. First of all, hats off to somebody who made their own mirror.
Yeah, I was going to get to that.
That's fabulous stuff. Fantastic. I hope that telescope that finally got onto its mounting in the 1980s has brought much pleasure. It's great stuff. But the question is absolutely right. Singularity is a term. It's a term that we sort of glibly use to describe a point with an entity with zero dimensions, zero physical dimensions, which is what a black hole is. Black hole is defined as a point of infinite density in space, and that the infinite density becomes because there's zero volume. Density is mass over volume. If the volume is zero, then the density is by definition infinite. But it's our listener is absolutely right. We've no idea what goes on in one of these infinitely dense points. I guess it's because we can't describe it that the singularity, in other words, something in space where physics doesn't work. That's the best term that's basically been adopted to describe it. But in terms of our understanding of what's going on inside it, yes, physics doesn't help because we don't have quantum gravity theory, exactly as we've just heard, and we don't have relativity. Doesn't handle this kind of these things. A dimensionless point. Relativity relies on there being a smooth continuum of space, but there isn't that at the singularity. It's something else. So a very well made point, and I agree. Yes, I agree.
Yeah, but we've got to call it something.
We've got to call it something. Yeah. Could call it.
So if relativity and physics don't work in a singularity or a black hole, could that lead the way to proving Einstein's theory of relativity does have a flaw in it? I mean, he always thought there was, and as yet we've tested and tested and tested it and found that it's rock solid. But
yes,
maybe a singularity is where we will find the whole thing unravel.
Well, it is. That's exactly right. And that's why we know there's a problem, because relativity won't let you deal with a singularity. And it's kind of incompatible with quantum theory as well. So this is a big hole in relativity, but everything else that relativity predicts is absolutely on the money at this very high level. 1 part in 10 to the 18 is one of the agreements. Actually, it's probably out of date now. It's probably 1 part in 10 to the 22 or something like that it agrees with an accuracy of that level. So it's still... it's as yet something that we have not found the chinks in, but there must be chinks because of the fact that singularities apparently exist in the form of black holes.
I suppose my point is that finding the chinks in a stable environment, I don't know, where we are might not be possible. We might have to visit a black hole.
No, you put your finger on something absolutely right, Andrew. That's one reason why it's so exciting that the Square Kilometre Array radio telescope's being built, because one of the things that telescope will do is investigate pulsars, which are spinning neutron stars. And neutron stars are one place where gravity is extreme. It's not quite as extreme as a black hole, but it's an extreme location in terms of gravity. And that's where the chinks might show up, rather than in the environment that we're living in, a pleasant, gravitationally modest place here on the planet Earth. It's where gravity is high that we might start seeing the gaps. And that's why, it's actually why in a committee that I had to front up to a couple of years ago about ratifying the SKA treaty, why I gave them the astronomer at large's personal guarantee that this telescope will produce Nobel Prizes. Ooh. It's got a 50-year lifetime, this telescope, so I'm pretty safe, I think. But was that I was thinking of, that, that if we do find the holes in relativity because of observations made by the Square Kilometre Array, then, that's a Nobel Prize winning event. And I hope you and I are around to talk about it.
I hope so too. And thanks for your question about singularities. Don't like it, but we've got to call it something. That's where I sit. Yeah. All right. We'll take a little break from Space Nuts. More questions to come on this edition of the show. You're with Andrew Dunkley and Professor Fred Watson.
3, 2, 1.
Space Nuts.
Let's continue. We don't get too many questions from from our female listeners, but I'm glad to see we've got one today from Liz. I love this question too.
Good morning, gentlemen. This is Liz. I have a question for you in regards to the Big Rip. We know that the universe is expanding, and we can think about it as a rubber band, right? Essentially, at some point, many scientists believe that the Big Rip is going to happen, and what it's going to look like essentially is going to look like a snapping rubber band, right? Well, it will snap in two. Is it possible that our universe is a product of another Big Rip?
Oh, okay. So we've gone from possibly being inside a white hole to being the product of a big rip. And ultimately, well, not ultimately, but the latest theory is rather than a gnab gib where the universe stops expanding and collapses back in on itself, it's just going to tear itself apart instead. So the big rip.
That's so exactly as you said, Andrew, because since 1998, we've known that the expansion of the universe is accelerating. That's led people to look into the distant future when you've got this runaway acceleration. And it's runaway because it seems to be that whatever drives the accelerated expansion of the universe is proportional to the volume of space. So as space gets bigger, this energy that's driving the acceleration also gets bigger and accelerates it even more. So it's a kind of positive feedback mechanism. And that's why people have suggested that eventually gravitational forces of space itself, or the structure of space expanding, will be so strong that they'll pull planets apart, they'll pull atoms apart, and eventually they'll rip the fabric of space-time itself, whatever that is. I mean, we find it hard to envisage how space-time works in that regard. And so that's what's known as the Big Rip. I tend to think of it as the whole universe fracturing rather than a rubber band breaking, although I think that's as good an analog as any. But yeah, the idea of some kind of cataclysmic event of this kind spawning another universe, in other words, becoming somebody else's Big Bang, it's been around for a while. Perhaps the best known of these sorts of theories is Roger Penrose's idea of a cyclic universe that suggests that if you've got ever increasing black holes getting bigger and bigger, eventually they will become unstable and explode, and that might be the equivalent of a new universe being created. With the Big Rip, I think it's possible. My knowledge of this is pretty sketchy. I've never looked at the equations that actually determine what happens in the Big Rip. They're probably pretty fearsome, but I guess it is possible that some kind of event of this kind could create another universe, which is, as I said, it's a fairly common idea in the multiverse community of scientists who think there might be many universes. But whether exactly this one is one that's favoured, I'm not sure. Certainly the Penrose idea has received a lot of attention. Nobody believes it, of course, but people actually like studying it and looking at the details of it. I've said this before, I think, not Andrew, but Roger wrote a book on this stuff, which is approximately the same shape as your average brick. It's a very, very thick book, and it's in two halves. And the first half of it is the mathematics you need to understand the second half of it.
Oh, good grief.
So it's a fairly copious, I can't remember what it's called. I did have a go at it once, a long time ago. Yeah.
Yeah. Well, I mean, how do we go about proving there are multiple universes? That's probably the first question. Yep. I mean, how do you prove it? We only know of this one.
Yes, and you can suggest tricks that might let you detect the existence of another universe. One of them is if you could find some sort of signature in the cosmic microwave background radiation that was... So the background radiation is kind of random. It fluctuates randomly, temperature difference across the sky. But you can do statistical analyses and we can find what's called a power spectrum. But if you found what you might call coherent structures within the background radiation, like a ring or a circle or something of that sort, that might be telling you that this is some sort of interference from an external universe.
Yeah. Just having the conversation reminded me that there was a story recently that suggests that some evidence may have been found of a parallel universe, but I don't know if it's been kind of accepted as probable or it's just
yes, I know the
speculation of some kind.
I forgot what it was about, but I do remember the story. If you have X, then you've got Y, and Y is a parallel universe.
Yeah.
I can't remember what it was. We did talk about it.
Yeah. Well, I think it got published in some pretty reputable.
It did, yeah.
Publications, and so it might hold water. Who knows? Thank you, Liz. Lovely to hear from you. Let's go to a text question now. This one comes from John in New South Wales. I love this one. This is another sort of what if. If I assume I have a tunnel which starts at the North Pole, goes through the core to the South Pole, and I jump into the tunnel at one end and begin to fall due to gravity, 1, will gravity be the same all the way to the core, given that at any point as I get deeper, there will be less mass below? And 2, once I get to the core, will I continue back up the tunnel away from the core, or will gravity gradually pull me back to the centre of the core like a pendulum? And 3, if I become stationary at the core, will I then be levitated by forces acting on me from every direction out to the surface? Love that question, John. Let's just assume for a moment that you will not be burnt to a crisp at the centre of the planet.
Things are a bit hot in the centre.
Push that possibility aside for the time being. Will he continue to fall and come out the other side? Will he end up sort of swinging backwards and forwards and end up in the middle? And will he levitate?
All of the above, yeah. So it is a great question, and the physics are pretty well understood, although, as you said, in fact, the core is at 70 degrees Celsius or something. You've got to ignore that. But what happens is, so you've got this tunnel, you jump into it, and it doesn't have to be at the pole, it can be anywhere on Earth, as long as it goes through the middle. You jump into it, and you are pulled downwards by gravity, but it turns out that the gravitational force you feel is proportional to your distance from the center. So as you get nearer the center, you feel a lower gravitational pull. And eventually, when you're at the center, you are weightless. So yes, you will levitate because you're weightless in the middle. But by the time you get to the center, though, you're moving so fast that you whiz through the center and you come up through the tunnel on the other side of the center of the Earth, and you stop just as your head pops up out of the center of the tunnel.
So you could potentially get someone to catch you or grab the edge.
You could, yeah. If somebody grabs you, you're all right, because that's where your velocity is zero again. But if you don't do that, you fall back in.
And that'd be it, because you wouldn't come up as far the other side.
No, you probably would, actually. If there's no friction. If there was no friction, you would.
Right.
And the really interesting thing is that if that was the case, then you'd oscillate backwards and forwards from one side of the Earth to the other, with a periodicity which is 84.5 minutes. And it turns out that is what your orbital period would be if you could orbit the Earth, actually skimming along its surface. It's exactly the same. It's the same as the orbit period. That's just the way gravity works. It's beautiful symmetry, beautiful symmetry. But yeah, you oscillate with the same periodicity as what your orbit period would be.
So I assume you could do that on any rocky planet.
Yeah, well, that's right. Yes, yeah, indeed. I think it's any object which has got sort of spherical symmetry. So even if it's got different layers in it, as long as it's symmetrical like that, then this holds good.
Yeah. So without friction, you just keep going backwards and forwards.
Keep going backwards and forwards, yeah. With your every 89.5 minutes, your head would pop out of one end and you disappear.
So you just have to make sure that every few hours someone's there to hurl you a McDonald's hamburger or something.
Yeah, that's right. Yeah.
Although after a while, going to the toilet would prove a problem.
You need a tunnel burger, and you probably need a tunnel convenience as well.
Yeah,
tunnel restroom.
But there'd be no stopping unless, of course, they put a net over the hole so you could grab it when you got to the top.
That's right.
Or the other top, because they'd both be the top.
They'd both be the top. That's right.
Yeah, I love that question. Really good. Thank you, John.
It's a great question. Yeah.
Yes. All right, we've got another good question. We've got a lot of good questions today. This one comes from a listener in Belgium.
Hello, Andrew and Professor Fred. This is Robin from Belgium. I've been meaning to send in this question for over a year now and only just got around to it. So here it goes. With all the discoveries of exoplanets in different systems in our galaxy these days, I often see people get very excited about the possibilities of livable planets. Yet a lot of scientists seem skeptical of this because so many of them orbit red dwarf stars, which according to these scientists makes life very unlikely. So I understand that our sun is a much less common yellow dwarf star, hope that's correct, and possibly an uncommon one of those as well. So I was just wondering, I always hear about Proxima Centauri, but what is the closest sun-like star? And are there people, an agency, or a team somewhere in the world that purely focuses on finding and charting the more sun-like stars in our galaxy? We'd love to hear your thoughts on this. Love the podcast. Thank you guys for doing this. All the best.
Thank you, Robin. Lovely to hear from somebody in Belgium, and we'll be answering your question in about a year. Or right now, whichever comes first.
Or right now, yeah. So, yeah, it's a nice, very nice question that sent me to the web just to check which is the closest single star like the sun. Mm-hmm. The answer is it is a star called Tau Ceti, the constellation of Cetus the whale. Tau Ceti is at a distance of 12 light years from Earth.
It's not very far.
Not very far, no, that's right.
They're about to start up a bus route between here and there, in fact.
Maybe one day, because it has 5 planets as well, which are bigger than the Earth. They're not what you call Earth-like planets. They're between 2 and 6 times the mass of the Earth, those 5 planets. But one of them lies in the habitable zone, the Goldilocks zone. So it's, that's rather intriguing, a sun-like star with the planet in its habitable zone, but much bigger than the Earth. So I think it's about 5 times the mass of the Earth. So it's still the smallest planet found to be orbiting the habitable zone of any sun-like star. But yeah, a really interesting question. Just harping back slightly to the question itself, the reason why red dwarf stars are considered unlikely as the stars that have, it's considered unlikely that their planets might harbour life, is because red dwarf stars are known to emit these pretty lethal flares regular intervals. So flaring red dwarf stars are not likely to be somewhere where life could easily get going just because of the radiation field that would be around them.
Yeah. Now, you said the planet that you just described around that nearest sun-like star is the smallest one they've found so far in the Goldilocks zone. Is that what you said?
That's correct. Actually, I should probably qualify that because this is a 10-year-old article that I'm looking at.
But
so that is still, almost certainly no longer true.
Yeah, but it's still 5 times the mass of Earth.
Yes, that's right. So it's still a big one.
Technically speaking, we're the smallest rocky planet in the Goldilocks zone that's ever been found.
Ta-da! We are.
Which also suggests that if we want to go and move to another planet, none of these are going to work because they're too big.
They're too big, yeah, that's right. There may be smaller ones that have been found now. As I said, that's quite an old article that I was checking up on that. But the Tau Ceti is certainly the nearest sun-like star.
Well, I think the last count on exoplanet discoveries passed 5,000, didn't it?
It did, yeah. It's 5,000, that's right.
Wow.
It's quite extraordinary, really.
It is very extraordinary. But, the more we look, the more we'll find, and the more likely it is we will discover a Earth-like planet that's Earth-like sized in the Goldilocks zone, and we might find a prime candidate. There's got to be one out there somewhere, Fred.
Oh, yeah, I'm sure there are. Sure, there are many Earth-like planets in habitable zones. The question is, does that automatically mean that they harbour life? And that's the big question that we don't know. We don't know how life kicks off. So
yeah. Well, I'll go back to my theory that it's all the stuff of life exists. It's you've just got to get the recipe right.
Yes, that's right.
And you've got to have the right oven to make it cook.
Yes. Yeah.
And right now we're overcooking. on this planet.
We are, yes. That's another story, though.
It is another story, but yeah. Although I did, just as a by the by, I did see a really fascinating article the other day because one of the concerns about global warming is that the threat it holds to the survival of certain species. And polar bears came up in the story as being probably one of the most short-term threatened creatures on Earth because of the thawing of the ice. But they've found a colony of them in the Arctic that have survived for hundreds of years, cut off from the rest of the world because they've adapted to the lack of ice in their vicinity.
That's interesting.
So they have survived against the odds because of the circumstances they found themselves in. So there is hope. Nature has a way.
It does. It does.
If nature decides that humans are the problem, well, they'll deal with us too. I'm sure. Okay, we'll leave it right there. Thanks so much for your question, Robin. Lovely to hear from Belgium. I know we've got quite a few listeners in Belgium. This is Space Nuts with Andrew Dunkley and Fred Watson.
Roger, you're loud and clear here.
Space Nuts.
Our next question, Fred, is a text question. This comes from Peter in South Australia. He says, "Hello, Fred and Andrew. We have rocky ice and gas planets. We have rocky and ice moons, but have we ever found a gas moon? And if not, is it possible?" Peter in South Australia. Good question.
Isn't it a great question? That's right. So I think the answer is no.
Oh. Let me guess. Too small to hold its water?
Yeah. Well, that's right. So gas giants are they're giants because they've accumulated envelopes of what are actually lightweight gases, hydrogen and helium. And so in order to keep those gases, this is what makes them gas planets. In order to keep those gases, they've got to have a lot of gravity because they're lightweight gases. And so they've got to be big. That's the bottom line. So the physics of, planets and moons suggest that if you did have a gas moon, then it would be as big as its primary planet, and it wouldn't be a moon. It would be the two halves of a binary planet, basically a planet, two planets rotating their common center of mass. So that's a possibility. But the idea of just a gigantic planet and a gas moon don't work, because that gigantic planet, to be much bigger than its moon, would actually have enough mass that it would become a star. Because that's, it would turn into a brown dwarf probably, or it would be a brown dwarf. So I think the answer is no, that we can't have gas moons, because they'd have to be as big as their planets are.
Of course, Peter, the answer is no until we find one.
Until we find one, yeah.
Because how many times have we said, no, that's impossible, and then we've discovered something very weird.
Yeah, that's right.
There's all sorts of strange things out there.
I think the watchword is never say never.
Never say never, but realistically, probably not.
Yeah, probably not. That's a better way of putting it. Thank you. Thank you.
That's okay. Short question with a short answer, which doesn't happen often. Okay.
No, it doesn't.
This next one, though, this one is reminding me of scenes from science fiction movies and science fiction TV series that I've watched, because I've seen this exact situation portrayed several times with varying creative license involved. The question will become self-explanatory. This is one from Martin and Son.
Hello, Andrew and Fred. This is Martin Berman Gorvine, writer extraordinaire in many genres, with a brand new question for you. And it's very simply, how long would one survive in space without a suit and a helmet? This was inspired naturally by this question, by a discussion between me and my son of the relevant chapter in The Hitchhiker's Guide to the Galaxy, in which the heroes are tossed out of an airlock and survive for 30 seconds to be rescued. I contend that one would die immediately of exploding eyeballs and inner ears and messy stuff like that. Whereas my son seems to think that if you expel all the air from your lungs, you could somehow survive for a couple of seconds. So what's the answer? Can't wait to hear. Over and out.
Martin, you've opened up a can of worms, which is also messy, but looks like there's more to your question than meets the eye. And you might be surprised to learn that your son may be more right than you are. You're both right. I've seen this situation portrayed in many, many forms. Big fan of the TV series The Expanse, which I've watched start to finish every episode for all seasons. And there's a couple of situations where people are spaced as a punishment. They're sent out into space to die. They linger. They linger for a little bit. But then I think it was the movie Red Planet where one of the astronauts takes his helmet off, snap frozen, dead instantly. So which way does it go, Fred?
Yeah, it's very interesting. I think it's the son who gets the right answer on this one.
Son of Martin.
Son of Martin, that's
Why?
right. Whose name we don't know, but because of experiments that have been done on this. So as always, I sort of tracked down what I could find about this. There's a very nice article that was published in Scientific American, always a magazine that I've enjoyed, which was published on the 14th of February 2008. So it's visible on the web. And the title of the article is Survival in Space Unprotected is Possible Briefly. And the subtitle is, But Don't Linger in the Interstellar Vacuum or Hold Your Breath. And so that's what Martin's son was saying. If you expel all the air from your lungs, you've got some time at your disposal. Not much, but you've got some time. Okay. And so there's experimental evidence for this, not with humans, of course. And, this is something that probably considered pretty unethical by modern standards. But back in the 1960s, research was done on dogs, which were exposed to very near vacuum for up to 90 seconds. They always survived.
Really?
And indeed they did. During their exposures, they were unconscious and paralyzed. This is the bit that I guess is what prompted your comment, Andrew, and I'm quoting here from the article. Gas expelled from their bowels and stomachs caused simultaneous defecation, projectile vomiting, and urination. It was a pretty grim, messy occurrence, as you would expect.
So, yes, Martin, messy indeed.
Messy. They suffered massive seizures. Their tongues were often coated in ice, and the dogs swelled to resemble an inflated goatskin bag. But after a slight repressurization, the dogs shrank back down, began to breathe, and after 10 to 15 minutes at sea level pressure, they managed to walk, though it took a few more minutes for their apparent blindness to wear off. It's quite extraordinary. But if you make it more than 2 minutes, they usually died. So you've got 90 seconds that you might survive through. Apparently, chimpanzees can stand even longer exposures as well, up to 3 to 5 minutes. And that's sort of, that's along the line. They're much nearer to humans than dogs are. So
Ford Prefect's 30 seconds in the vacuum of space was feasible.
Was feasible, that's right. Yes, it was Ford Prefect, wasn't it? Yeah, yes. I remember that bit.
And who was the other guy? Oh, gosh.
What's his name? The hero.
Oh, no. 3 arms, 2 heads.
Oh, yeah. I can't.
People are screaming.
The only one I can ever remember is Slarty Bartfast, who was the man who he got the award for the fjords in Norway.
Yes, that's right. Oh, gosh. I need to know. I know now.
I do know who you mean.
I'm going to look it up.
His girlfriend she had a nice name as well.
Zaphod Beeblebrox.
Zaphod Beeblebrox. That's right, you got it. Well done.
And of course, the female hero of the show was Trillian.
Trillian, that's her.
Yes, Ford Prefect and Zaphod Beeblebrox were thrown into the vacuum of space by another name that escapes me, and they were picked up by a spaceship.
It was the Vogon constructively.
Vogon constructively, that's right.
Yeah.
Oh, we're such nerds.
We are nerds.
We're terrible nerds. There you are, Martin. So, yes, the answer is yes. You could probably survive for up to 90 seconds in the vacuum of space, which is a horrifying thought, especially with all that, liquid coming out of you.
Yes.
It wouldn't be nice. In fact, a rescuer would probably say, yes, he's alive, but I'm not touching him.
Yeah.
All right. Please tell your son that he was right and you were wrong, Martin. Well, depends. Okay, one more question to wrap it up for this week, and it's another question of, it's only a short question, this one. This comes from Duncan in Weymouth in the UK. I cannot recall if I asked this. I hope you did, and then I won't have to read the rest. I know I've sent you a few written questions that were too long to go in audio, but you have not done written ones for ages now. Yes, we have. We have today. You must have enough of them now from me to do a whole show. Yeah, we probably do. Anyway, I've seen lots of animations of the Milky Way and the Andromeda galaxy coming together. A couple of questions. People say that Andromeda is heading towards us at whatever the speed is. Is it true, or can we actually head towards each other? And what is more, is it more of a circular mutual center of gravity sort of thing that we're both heading towards in a decaying orbit that means one day we will impact each other? Secondly, what will happen to the Triangulum galaxy? I often read or hear that it is orbiting Andromeda, even though it is the third largest galaxy in the group, yet I've not seen any collision animations which include the Triangulum galaxy. Will it be thrown out of the local group, or will it be squashed between us, or what? Thanks for all your work. I listen each week whilst doing my hobbies, usually on YouTube. By the way, need more cats and cockerels, or cockerels, please. Maybe a T-shirt with a cat in a spacesuit at the centre of the Space Nuts logo. Thanks, Duncan in Weymouth in the UK. And I think Duncan also wanted to know if you could get a T-shirt sent to the UK from our website. The answer, according to Hugh, is yes. You can. So, go ahead and hit the Space Nuts shop, Duncan. Yeah, all right. So what's the scenario? I mean, we're not just heading towards each other in a straight line, I assume. So is it more of a dance that's going to bring the Milky Way and Andromeda together? And what's going to happen to the Triangulum galaxy?
Indeed. So these simulations are pretty easy to find on the web. And what they show is that, yes, it's almost a head-on collision, even though probably will, that when you think about, because galaxies are pretty big things, if you're thinking about the nucleus of each of the galaxies, they probably will be slightly offset and do a bit of spiraling around one another. But yes, the simulations all show vast disruption to the galaxy. They kind of overshoot each other, Andromeda and the Milky Way, sort of pass through each other, basically, and then are pulled back by gravitational forces and eventually settle down into a fairly featureless elliptical galaxy. This is in several billion years, like about 8 billion years' time, which is usually being called Milkomeda because it's the Milky Way and Andromeda merged together.
Well, that's better than the other option, which would be Amway.
Yes, it would. Amway. No, there's a blast from the past. Anyway, I think actually Milkomeda gets formed, roughly 6 billion years. So the collision's about 3.5 to 4 billion years time, and then it settles down a couple of billion years later. So that you've got Milkomeda, the resulting elliptical galaxy. But Triangulum, apparently throughout many of the simulations, it just continues to orbit both of them.
Oh.
So it's sort of a bit out of the way, although I know there are some simulations that show it will be part of the collision. Yeah, it might get stuck between them or something like that. But I think most of them show Triangulum surviving more or less unscathed from all this.
Okay.
I guess a lot depends on how long your simulations go into the future. Most of them stop at about 8 or 9 billion years. So it's I haven't seen any of those simulations that do include the the triangular. So even though some models predict that it won't survive, I haven't seen any evidence in terms of computer visualizations that that's the case.
Okay. And we should point out to Duncan that when all this happens, it's not going to be cataclysmic. It's just going to be a very slow merger, I suppose.
Yeah. Yeah, and there's so much empty space in galaxies that it'd be very rare for stars to collide. What will happen is that the shock waves that are produced in the collision the fact that there are gas clouds in both these galaxies, they're both fairly gas-rich galaxies, they will spawn a burst of bright star formation. Bright stars mean stars that don't last very long, big ones, and they will end their lives in supernova explosions. So it might get a bit hot in terms of the radiation environment, even if the stars don't collide with one another. With all those supernovae going off as a result of the star formation triggered by this collision, you'll probably get much higher levels of radiation otherwise had, which could be dangerous for any living species on any of the planets of the stars.
Well, that's no good.
No, it's no good, is it? Yeah.
No, I'll scratch it out of my diary now. I don't want to be there.
Yeah, you don't want to be there.
And thank you, Duncan. Hopefully that covers your question, and thanks for asking. You up for a question without notice, Fred?
Take it to 10.
Yeah, why not? We'll go to 10 questions for the episode.
Yeah.
All right, here it is.
This is Bob again from Asheville, North Carolina in the U.S. During last week's program, Dr. Watson said he received his PhD in Edinburgh, Scotland. I was once again impressed that he seems to have been everywhere, met everyone, and know everything. Would Dr. Watson be able to summarize his academic career and mention some of the highlights of his work as an astronomer? Thank you. I love the podcast.
Yeah, I threw that in because I know we've only got a few seconds left, but I thought you could answer it.
Oh, dear. So, well, the short story is that, I was completely fascinated by astronomy as a kid. Took myself off to Scotland's oldest university at St Andrews, where they had been teaching since 1413, and you could tell because they had similar methods. They didn't execute you if you failed your exams anymore. But
that's good.
In the early days, got my degree, but I spent 2 years working for a company that built large telescopes, including the telescope I was later astronomer in charge of. The Anglo-Australian telescope and the UK Schmidt telescope. I worked for them for a couple of years as an optical physicist. Then went back to do a master's, back to St Andrews, master's in asteroid orbits. Worked at the Royal Greenwich Observatory on planetary orbits for a while. Then went to Edinburgh, the Royal Observatory in Edinburgh, to work on star orbits around the centre of our galaxy. And in fact, that was where I got my PhD, because I then came out to Australia with this stupid idea that you could put fibre optics on telescopes and do all kinds of things that you couldn't otherwise do. That's what got me my PhD. It's what kept me in Australia, because it turned out to be so important in the astronomical world. And nowadays it's big business building instruments that use fibre optics. So my studies have been across the board, really. Asteroids, stars, done a lot of survey astronomy where you're looking at different kinds of objects, whether they're stars or galaxies. I was project manager for the International Rave Survey, the radio velocity experiment, and many other things of that sort. And it's been a ball, actually. I don't do much research these days. I sort of...
Well, that's because you know everything, Fred.
No, it's because, who wants an old gimmer who doesn't have much to contribute? But it does give, maybe my mixed career is why this sort of thing's possible, because I've been involved in so many different branches of astronomy and the technology of astronomy. And I've loved it all. Honestly, Andrew, I have had a ball. And long may it continue.
Well, I think under that the job advice that your school counsellor would give you, find something you love and get a job in it, is
that's right.
Your photo is next to that statement.
Yes, that's right.
And I can claim the same thing, working in radio. I feel very privileged and lucky. And I'm glad you and I got together and started doing these discussions on radio and on the podcast, because it's a lot of fun. And it's clear to me that a lot of people really enjoy getting the information in this form. So happy to provide it. And thanks for asking the question, Bob. I couldn't help myself. All right. That brings us to the end of another program. Fred, thank you very, very much.
It is my great pleasure, and I hope we'll do it again next week.
I believe we will be, yes. It's in my diary right there next to the collision with Andromeda, which might be a bit later than next week.
Yeah, that's right.
Yes. Now, just a reminder, if you do have questions for us, I mean, we've got a bit of a stockpile at the moment, but we'll get through them. And if we haven't answered them before. So go to our website, spacenutspodcast.com or spacenuds.io, and there's a couple of ways you can send us questions through the AMA link or send us your audio question tab on the right-hand side, and we'd be happy to have a crack at some of those. Just send them in whatever format. Don't forget to tell us who you are, because we do like to know your name. So that we can write to your school principal and tell them that you're loafing. And while you're there, check out the Space Nuts shop. And in fact, click on all the tabs, because it's just like sort of bursting bubble wrap. It's just so much fun. But anyway, visit our website, send your questions in, and check out the rest of our pages while you're there, spacenutspodcast.com. That brings us to the end of episode 310. Thanks so much for joining us. We look forward to your company on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.